Let's say I shine a flashlight right in your eyes, because I'm one of those teachers who thinks irritation is a path to knowledge. You'll cover your eyes right away. You certainly won't see that I'm shining it at you, wait 5 minutes, and then lift your hands up slowly to cover your eyes. That's because the speed of light is extremely quick. It takes a fraction of a second for the light from my flashlight to reach across the room. It's so fast that it seems instantaneous, but it's not. The speed of light is a specific, measurable speed, and we can use the Michelson interferometer to measure it. A Michelson interferometer is a device that takes a beam of light, splits it into two separate beams, and then recombines them into a single beam again. This might seem like a pointless process, but by splitting the light up, you can do one thing to one beam and something different to the other and see how it affects the results. Mirrors are usually used to accomplish this. A half-silver mirror is a surface where half of it is coated in mirror material and the other half is transparent glass. This allows half the light to be reflected and half to go straight through. This is the simplest way that we can split light into two separate beams. Regular mirrors are also used to redirect the beams in whatever way we need. As you can see from this diagram of a Michelson interferometer, half the light is reflected at 90 degrees by the half-silver mirror, and the other half goes straight through. Mirrors are then used to bounce the light back and recombine them into a single beam that goes to a screen or a detector. But why do we do this? What does it help us discover about the world? To answer that question, let's take a look at the history books. Before the first Michelson interferometer was used by Michelson and Morley, people weren't sure if the speed of light was really a constant. Maybe it changed in different circumstances, or perhaps it was different in one direction than it was in another. The reason they thought it might be different in each direction is that a lot of scientists still thought that the universe was made of something called the luminiferous ether. This is an invisible medium that light was believed to travel through. After all, water waves traveled in water, and sound waves traveled in air, so surely light waves must also have a medium. If such an ether existed, it was expected to be moving in one direction or another, and so the speed of light would be different if it were moving with the ether than it would be if it was moving against it. Nicholson and Morley tested this using their interferometer by splitting the beam of light and making each part of it travel in a different direction. When the two beams of light were combined back together, if they traveled at different speeds, they would see interference patterns. Interference patterns are a mix of light and dark spots or lines that you get when two waves, in this case light waves, are no longer in phase, when the peaks of the two waves don't hit the screen of the detector at the same time. Nicholson and Morley put their interferometer on a turntable and pointed it in lots of different directions. They also waited until different times in the Earth's rotational orbit. But whatever they did, they saw no change in the image on the screen. It seemed that the speed of light was constant in every direction. This knowledge eventually led to Einstein developing the special theory of relativity, and with it, a revolution in physics began. There are many other useful experiments you can do with a Michelson interferometer. By splitting the beam of light into two, it allows you to do different things for two parts of the light and see the results. So you can put one beam of light through one material, like a pane of glass, and the other through a different material, like, say, argon gas, and then see which beam of light travels faster. While the speed of light is the same in every direction, putting materials in the way does change the speed a little. You can also use an interferometer to more precisely measure the exact position of an object, to split light up into a spectrum, as a spectrometer, to test optical components, and to study wind and temperature patterns, especially in the upper atmosphere. A Nicholson interferometer is a device that takes a beam of light, splits it into two separate beams, and then recombines them into a single beam again. Mirrors are usually used to accomplish this. A half-silver mirror is a surface where half of it is coated in mirror material and the other half in transparent glass. This causes half the light to be reflected and half to go straight through. By splitting the light up, you can do one thing to one beam and something different to the other. Nicholson interferometers can be used to measure the speed of light in different mediums, precisely measure the exact position of an object, break light up into a spectrum, test optical components, and to study wind and temperature patterns, especially in the upper atmosphere. The first and most famous use was to test for the existence of the luminiferous ether, which is an invisible medium that light was believed to travel through. This was tested by splitting the beam of light and making each part travel in a different direction. When the two beams of light were combined back together, if they traveled at different speeds, they would see interference patterns. Interference patterns are a mix of light and dark spots or lines that you get when two waves, in this case light waves, are no longer in phase, when the peaks of the two waves don't hit the screen of the detector at the same time. Even after rotating the equipment and trying different times of day and year, Nicholson and Morley saw no change in the image on the screen. This proved that the ether didn't exist, and the speed of light was a constant in every direction. A revolution in physics began soon after when Einstein used his theory of special relativity to explain how the universe and light really work.